All right. So hello, everyone. Welcome back. So I finally did get back the chapter 1 homework to you, so you can check your email for that. All right. Yeah, I already have a question about that. Okay. So if you have a quick question about the grading, I can address it now. Well, I'm not rushing too much today because we do have I do have some time set aside for homework in general today. So in fact, so what's the plan, by the way? So today is October 22nd. It's good to look at the calendar to see what's going on. All right, so today's Thursday, October 22nd. It helps me to do this to remember what day it is. My MacBook does tell me. All right, we're gonna continue with chapter 5, and although the chapter 4 homework is due next week, and only the chapter 4 homework, still you should keep up with chapter 5. And also, what we do today will help on this homework actually. Okay, in particular, 5.3 especially, we're going to start talking about solving trig equations in earnest, and that does help you with some questions in chapter 4. I believe in 4.7 I have some questions about how to solve basic trig equations. All right, and in 5.152 we reinforce analytic trigonometry on the algebra of trig. All of this is analytic trig. Chapter 5 in general is on analytic trig. All right, chapter 6 is miscellaneous. Now the chapter 4 homework is due next Wednesday, October 28th. So again, today we're going to continue with chapter 5, which will help with chapter 4 as well. I should have some time for homework, questions, all right, and I'll go after class as well. And then next Tuesday, I'll spend the whole session discussing the chapter 4 homework. And as you saw in my grading, keep an eye on that attachment. It turned out that 3 of the 4 problems that I graded rigorously, there were actually corresponding bits in the video. And in fact, that does kind of make sense. It makes sense that there would be a correlation. And in fact, I reserve the right, as I said in my note, I reserve the right to adjust my grading scheme for the homeworks in the sense that, I might actually start with looking at the videos maybe, and that might help determine which ones I grade. Of course, I may have some others that aren't in the videos, but it makes sense to me that some of the ones that I grade are in the videos. That would make sense to me, right? But anyway, next Tuesday we'll spend the whole session on chapter 4 homework, or chapter 5 also if you wish. And then the homework is due on the following day, Wednesday, October 28th, and then we'll continue on with chapter 5 on solving trig equations, and then the advanced trig identities, which you would have to know if we had exams, but I hope you do know them anyway. All right, that's the plan. And now we continue in grading the rest of the semester. All right, let's see. All right. Any general questions, like for example, general questions about the grading? If you have particular issues, then we can discuss after class, perhaps. Okay. Any questions before we begin? Any questions before we rejoin chapter 5 on analytic trig? Analytic trig. We're going to start with simplifying trig expressions. Continue with that. Then we're going to verify identities. It's more fun than you're used to. I have a good video on that, and we'll start 5.3 on trig equations. Okay, so we're recording now. All right, let's begin. Okay, we are recording.
Hi, everyone. We're continuing with section 5.1 on using fundamental trig identities to simplify trig expressions. Before, we broke things down into sine and cosine as a strategy. Now, we're going to consider factoring. Our old school algebra still works. So for example, let's simplify sine squared of x. It's good to put parentheses, by the way, to make arguments very clear, especially here. Let's simplify sine squared x plus sine squared x times cotangent squared x and try to write this as compactly as possible. Now, actually, like in the previous example, it might be easier to use the quotient identities first and break this down into cosine and sine. That could be easier. But let's try factoring as a strategy. Now notice here, a substitution might help. You can do this mentally. For example, if we let A be sine of x, and we let B be cotangent of x, then this here has the structure a squared plus a squared b squared. I might write it out. A squared plus a squared b squared. You could do a snap substitution. This is really of this form, where a is sine of x and b is cotangent of x. And for some students, it might be helpful to focus on this algebraic form here instead of blending in the trig. How do you factor a squared plus a squared b squared? You can factor out the GCF, which is a squared. You get a squared times the quantity, don't forget the 1, plus b squared. This could be like side work. And then you could sub back. Again, you could do this mentally. Basically, you end up with, well, a squared becomes sine squared x. 1 plus b squared becomes 1 plus cotangent squared of x. You don't have to actually perform this substitution. You can just write the left side out as the right side as one step without showing that work. You're basically factoring out sine squared x, and the other factor is 1 plus cotangent squared x. Now, how can we rewrite 1 plus cotangent squared of x? 1, the square of a trig function? We might be smelling Mr. Pythagoras, a Pythagorean identity. What is 1 plus cotangent squared of x? It is cosecant squared of x by Pythagorean identity. On my homework, you won't have to write this out, but I hope you know it's by Pythagorean identity. Okay, some instructors have people write that out. All right, now we can use the reciprocal identities, or just the old school strategy of breaking things up into sine and cosine, which we could have done early on. How can we express cosecant squared of x in terms of sine of x and cosine of x? Or another way of looking at it, how are these two expressions related? Wait a minute, they're reciprocals. Cosecant squared of x is the reciprocal of sine squared of x, and lo and behold, sine squared of x divided by sine squared of x equals 1, provided that sine of x is not 0. That is technically a hidden restriction. Sine of x is not 0, or more precisely, x is not of the form pi n, for integer n, if you want to be more precise. Bottom line, this expression here boils down to 1. So as long as x is not a value that makes sine of x equal to 0, if x equals pi over 3, pi over 4, certainly any non-quadrantal angle, then this ends up being 1. So if I were to ask you, what's the value of this when x equals pi over 6? Bottom line, it's 1. It simplifies very nicely. And it's undefined for these values of x over here. Now, if you were to graph y equals this, technically you'd get that. You'd get the graph of y equals 1, but you get holes for values of x where sine of x is 0. And x equals integer multiples of pi, 0, pi, 2 pi, and so forth. This is really the graph of y equals this over here. Basically, the line y equals 1 with holes on it. But again, that issue with the holes and the hidden restriction, we tend not to worry about these things so much in Chapter 5. So certainly, we simplified here. Okay, let's try this one. Simplify 1 minus 2 cosine squared x plus cosine to the 4th x. And again, some students might benefit from a substitution. Let u, let's say, equal cosine of x. And then this becomes, after the substitution, 1 minus 2u squared plus u to the 4th. And you might recognize this as a PST. It turns out that this is the square of 1 minus u squared. It's 1 minus u squared times itself. From here to here, some students might even benefit from a double substitution. Let w, let's say, equal u to the 2nd. And then this will be more clear. Now, you might be tempted to factor this. Actually, we often like squares of trig functions. You wonder why? So instead, why don't we go back and plug in cosine of x for u right now? Let's go back to x. So we have now the square of 1 minus u squared is cosine squared of x. And hey, look at this. What is 1 minus cosine squared of x? It is sine squared of x. Says who? Says Mr. Pythagoras. 1 minus cosine squared of x equals sine squared of x. And then it comes down to basic algebra. What is the square of a squared? A squared, all to the 2nd, is a to the 4th. I'm doing a snap substitution. A equals sine of x. So this becomes sine to the 4th x. In fact, these two expressions are perfectly equivalent. There are no hidden restrictions. The domain is all reals for both the original and this. You could use Desmos to check these out. They're going to have the same graphs. So for example, what is the value of this when x equals 0? Quick. Well, plug in 0 here, you get 0. It's a lot faster to evaluate this bottom guy. Simplification is your friend. And again, in calculus, when you're taking derivatives and integrals, it's easier to work with that than with that. Factoring. Factoring still applies. Factoring still works. Next up, how do we manipulate fractions? Basically, how do we manipulate sums and differences of rational expressions in these trig functions? Next time.
Okay, so make sure you're not too rusty with factoring. Be able to recognize maybe PSTs, right? Maybe some old school factoring, but factoring still applies, and if necessary, do a substitution. All right, questions? Questions? Feel free to put questions in chat. Great.
Hi, everyone. We're continuing with using fundamental trig identities to simplify trig expressions. We're now going to add and subtract fractions, namely rational expressions in trig functions of x. All right, let's simplify this. 1 over secant of x, it's good to put parens. 1 over secant of x, that plus 1, minus 1 over secant of x, that minus 1. Now, in my notes here, I don't do a substitution, but I think a substitution might be helpful. So let's go ahead and let u be secant of x. Let's let u be secant of x. And then this here is of the form 1 over u plus 1 minus 1 over u minus 1. And let's proceed from there. So now we're looking at the algebra. We're leaving the trig on the side for now. We're focusing on the algebra. Okay, first of all, we'd like to get a common denominator, the least common denominator, the LCD. These two bottoms are relatively prime, so we're going to take their product as the LCD. The quantity u plus 1 times the quantity u minus 1. Just like if we had 1/2 minus 1/3, then we take 2 times 3, or 6, as our common denominator. All right, so we want to build up these fractions so that the new bottom looks like the LCD. And how do we do that? All right, so for the first fraction here, who's missing? Who's missing from this first bottom to get the LCD? I need a u minus 1. He's missing. So I need to multiply the bottom by u minus 1. That means I also have to multiply the top by u minus 1. That ensures that I'm multiplying by 1. Likewise, over here, who's missing down here? The u plus 1. So I multiply this fraction by u plus 1 over itself. That is, I multiply by 1. And then I'm going to end up with a common denominator, which is the product of u plus 1 and u minus 1. It's the same product over here, just in a different order. But what is the quantity u plus 1 times the quantity u minus 1? It's going to be u squared minus 1, a basic algebra rule. U plus 1 times u minus 1, that gets us u squared minus 1. On the tops, we have u minus 1 minus, don't forget to put the grouping symbols, minus the quantity u plus 1. Now over here, I technically have the right to not put parentheses because the fraction bar implicitly groups the top and the bottom. But the one good thing about putting the parentheses in, aside from it being visually appealing, is that it reminds us that when we subtract this numerator, we need grouping symbols, the quantity u plus 1. So let's work out the top, simplify. We get u minus 1 minus u minus 1. That's a minus over here. See, if students make a mistake and they put a plus 1, they end up with a 0 on top and they get very confused. So what happens when we simplify the top? Well, the u and the opposite of u do knock each other out. We get 0 from u and the opposite of u. Negative 1 minus 1 is not 0, it's negative 2. So we get negative 2 over u squared minus 1. And this basically finishes the key algebra phase of this problem. You might be tempted to factor the bottom, but then you'd be kind of going backwards. And actually, we like having u squared there because we like having squares of trig functions. And remember why. Let's go back from u to secant of x. U was secant of x. Remember in my notes, I didn't do a substitution. I just used secant of x, which is fine. Build up the fractions, get a common denominator, group over here. These cancel out. So we have negative 2 over, again, u squared, which is now secant squared of x, minus 1. But we're not done yet. We have the square of a trig function. We have a negative 1. We might be smelling Mr. Pythagoras, a Pythagorean identity. And in fact, a Pythagorean identity will help us. It turns out that if this were a plus 1, an identity wouldn't be so helpful. But the fact that secant squared of x minus 1, it does turn out that an identity will help us simplify. Now, who's the partner here? What was the squared trig function that went with these guys? Secant squared of x and plus or minus 1. It was tangent squared of x. But is this equivalent to tangent squared of x? Do we have the right sign here, for example? Well, let's see. What was that Pythagorean identity that involved these trig functions? It was, remember, we're trying to replace this over here. Secant squared of x minus 1. Is that tangent squared of x? Let's see. The Pythagorean identity said that 1 plus tangent squared of x, or vice versa, equals secant squared of x. So the goal is, how do we get this bottom, secant squared of x minus 1? I can get that by subtracting 1 from both sides. Secant squared of x minus 1, which was the bottom here, is equivalent to tangent squared of x. In fact, they even have the same domain restrictions when cosine of x is 0. So we can replace secant squared of x minus 1 by tangent squared of x. So we have now negative 2 over tangent squared of x. But we're not quite done, because we want to try to avoid fractions here. What is the reciprocal of tangent squared of x? What does this basically hop up as a factor? The answer ends up being negative 2, and then this hops up as the reciprocal, cotangent squared of x. If you don't believe me, remember, you can write this as negative 2, or negative 2 over 1 if you wish, times 1 over tangent squared of x, kind of peeling this apart. Again, the reciprocal of tangent squared of x is cotangent squared of x. So that big, ugly expression way up here ends up simplifying to negative 2 cotangent squared of x. Much, much simpler. That's as compact as we can get it. We can't do much else to make it better. Next up, trig substitutions.
Well, okay, we had a lot to do there. Okay, so would anyone like me to review that? All right, and by the way, you don't technically have to do this step here. If you go straight from here to here, I'll believe you, but this might clarify matters for some students. It explains why this thing hops up as the reciprocal. Questions? Questions? Right.
Hi, everyone. In 5.1, we're going to use trig substitutions for algebraic expressions and then simplify the result. So in calculus, you may be asked to integrate something like this, an algebraic expression in x. And you actually want to introduce trig. In this case, we want to use a trig substitution, x equals 4 sine of theta. Here I'm being nice. I'm telling you the trig substitution we want to use. In your calculus class, you may have to remember what to do and figure out what the substitution has to be. So what we're going to do now is we're going to substitute 4 sine of theta in for x here, and then simplify. We're going to assume for now theta is acute. All right, we start with the square root of 16 minus x squared. We substitute x with 4 times sine of theta. When you square a product, you square each factor. The square of 4 sine of theta is 16 sine squared of theta. And then, what can we do to that radicand? What can we do here? We can factor out a 16 inside the radicand. And we get what? We get the square root of 16 times the quantity 1 minus sine squared of theta. And how can we simplify 1 minus sine squared of theta? That's cosine squared of theta, says Mr. Pythagoras. And by the way, the 16 pops out as a 4. The square root of 16 is 4. 1 minus sine squared of theta is cosine squared of theta. The square root of 16 is 4. The square root of a product is the product of roots. These are non-negative. So we have 4 times the square root of cosine squared of theta. Now, technically, what's the square root of x squared in general? In general, it's not just x, it's the absolute value of x. So technically, we should start by saying that this becomes 4 times the absolute value of cosine of theta. But now wait, we're assuming theta is acute. And if theta is acute, that means that cosine of theta has to be positive. The absolute value of a quantity that's known to be positive is just itself. So this does simplify to 4 cosine of theta. Again, the square root of 16 minus x squared after you perform the substitution ends up being 4 cosine of theta. Now I want to show you something else. So here's our trig sum, x equals 4 sine of theta. So how can we express theta itself? Well, if x equals 4 sine of theta, we can then say that if we divide both sides by 4, we can say that x, I'll do this in a different color. I'll do this in blue. If x equals 4 sine of theta, we can then say that x over 4 equals sine of theta. And then if theta is acute, we can go ahead and say that theta is going to be the inverse sine of x over 4. And as you do this calculus problem, you may end up having to work with, I don't know, maybe the cosine of this or the tangent of this at some point. Well, guess what? Remember, over here, we dealt with those kinds of expressions. Remember this guy here? Cotangent of inverse cosine of x over 3. That's when you get these kinds of expressions, when you get like the cosine or tangent of something like this, and then you can simplify this algebraically using the technique we discussed earlier in 4.7. And you get an algebraic result. Because remember, we started with an algebraic expression. So it all ties together. You're going to do all this stuff in Calc 2. The technique of integration by trig substitutions. Next up, we're going to verify trig identities in 5.2.
Right. So I know some of you are apprehensive about trig identities, but they're fun. Once you get used to them, they're fun. All right. And so it was hard for me to come up with videos for this chapter, but when it comes to identities, I came up with this. All right, verifying trig identities. 5.2.
Hi everyone, we're going to start section 5.2 on verifying trig identities. Now this is both harder and easier than section 5.1 on simplifying trig expressions. It's harder in the sense that we tend to deal with more complicated expressions in these problems. It's easier in this following sense. We're basically simplifying. Like for example here, we're going to simplify from the left side to the right side. But this time, unlike in 5.1, I'm giving you the answer. So in that sense, 5.2 is easier, but we're dealing with more complicated expressions. So it's a bit of both. All right, let's verify this identity. I claim that this statement holds for all real values of theta as long as we don't have a domain problem. And in section 5.2, we're going to sweep domain issues under the rug pretty much. All right, now, in these verification problems, you need to choose which side to start from, the left-hand side or the right-hand side. And then, so starting at one side, you're going to proceed and simplify that side until you obtain the other side, verbatim, exactly as it is. Many students like to do a little bit of work on both sides. That's okay to help prepare yourself, but in the end, you really should start at one side and indicate which side you start at. Maybe by typing in something like, or writing in something like LHS for left-hand side, or RHS for right-hand side. Usually, we start with the longer, more involved expression and then trash compact it down to the smaller, more compact expression. Although that's not always the case. I would say, though, that if you try to blow up the right-hand side to match the left-hand side, you might have to be more creative. But in this problem here, we're going to start at the left-hand side and try to obtain the right-hand side verbatim. I'm going to think of this as the target. It's a target that we're aiming for. Imagine the top of a jigsaw puzzle box. we're aiming for that target. And keep that in mind. Now, I present to you 4 solutions to verifying this identity. Actually, it took me 4 tries to get me my best solution, which is not even in my notes. I'm going to show you my 4th and best solution now. Now, bear in mind, on your homework, on exams, you may not have to give the absolute best solution from the book. This is often referred to as kind of God's book, where all the best proofs and solutions are. You don't have to give me the perfect solution here, but try to avoid giving me something that's 10 pages long when 4 lines would do. It turns out that it took me 4 tries to get me my best solution, and I'll show it to you now. Now, with all 4 of my solutions, I start with the left-hand side. It's the longer, larger, more complicated side. We normally do go from the larger expression to the smaller expression, though not always. Sometimes we do go smaller to larger, but usually we go larger to small as a strategy. All right. Now, a key strategy, which I came up with kind of down the line, internal consistency. Now, what do I mean by this? We often help ourselves by making these pieces look like each other. In my first attempt at attacking this problem, I did what a lot of students did. I broke this down into sine of theta and cosine of theta, and I'll show you the result of that soon enough. But it turns out that my much more efficient strategy over here appeals to the idea of internal consistency. Make these pieces look like each other. And by the way, target the target. Aim for the target. That's another strategy. Aim for the target. And keep that in mind. We want to aim for the target. So in my solution number 4 here, I indicate that I start with the left-hand side. You should either copy the left-hand side outright or just write LHS to clearly indicate which side you're starting at. Now here's my strategy in my solution 4, my best solution, I think. My strategy here is to make these pieces look like each other. Now, a lot of students would be inclined to make cosecant of theta look like sine of theta, and to make cotangent of theta look like tangent of theta. Cosecant of theta is 1 over sine of theta, for example. But remember that we want to aim for the target. We want to aim for cotangent of theta times cosecant of theta. Instead of making the top pieces look like the bottom pieces, it may be more strategic to make the bottom pieces look like the top pieces. Again, we can use reciprocal identities. But this time, we're going to use the fact that sine of theta is the reciprocal of cosecant of theta over here. And in the bottom left, tangent of theta is the reciprocal of cotangent of theta. So this might look a bit strange because you may be used to expressing bigger trig expressions in terms of what you think of as easier or nicer trig expressions. We may be more familiar with sine of theta and tangent of theta than these 2 guys up here. But remember, we also want to aim for the target. In the end, we want to end up with cotangent of theta times cosecant of theta. So it may be better for us to make the bottom guys look like the top guys, which I do here. All right. So now we have a compound expression. We need to make this a lot simpler. Well, there are different strategies. Some students might want to get a common denominator for these 2 fractions down here and make this bottom denominator, this denominator here, into a single fraction. That's totally legal. Maybe multiply this by cosecant of theta over cosecant of theta, and multiply this fraction by cotangent of theta over cotangent of theta. That would work. In my document here, I try a different strategy. I take the overall LCD, which is the product, really the LCM, the least common multiple, of these little denominators over here, cotangent of theta and cosecant of theta. They don't really have anything good in common. They don't have much in common besides plus or minus 1. So I'll take their product as the overall LCD. And I'm going to multiply the top and the bottom by this LCD, this overall LCD, the product of these two little denominators. My goal is to ultimately clear these fractions down here. So I'm going to multiply this fraction by 1. Again, don't worry about domain issues right now. I'm going to multiply by 1 in the form cotangent of theta times cosecant of theta times itself.
Over itself. I put that correction in YouTube already.
The goal being for this product down here, when it distributes through, I'm going to clear the fractions down here. Now in the top, you might be tempted to distribute in the top. Many students like to apply the distributive property because they like to show off. They like to show off what they know. But it turns out that distributing up on top will just waste your time. You're going to have to factor back like this anyway. So don't distribute just because you feel like it. On the top, we're not going to distribute cotangent of theta, cosecant of theta into these two terms. You're just going to make a mess and you're going to have to factor back later on. We like factored forms. We like factored forms provided that the pieces are fairly nice. Down here, when you look at these denominators, look at this denominator of this compound fraction. We don't like the fact that we have these fractions inside the denominator. That's why we have a compound fraction over here. So I actually do want to apply the distributive property and distribute cotangent of theta, cosecant of theta into these two terms here. I want to distribute. Because multiplication distributes over addition, I'm going to hit both of these terms by these two factors, cotangent of theta times cosecant of theta. The goal being to kill the denominators down here, the little denominators, and to avoid a compound fraction after this point. So again, do not distribute on the top because we like factored forms when the pieces are nice, but we are going to distribute in the bottom because I don't like these fractions here. I don't like these little denominators. So let's clear them. All right. Again, on the top, I'm going to multiply them, but I'm just going to indicate them in factored form. The factor, cosecant of theta plus cotangent of theta, okay, times this thing we're multiplying by, cotangent of theta, cosecant of theta. I'm going to indicate this product, but I'm not going to distribute because that'll be a waste of time. If we distribute, we'll just make a mess of things, and we're going to end up having to factor back anyway. Remember, we like factored forms because we're hoping to cancel later on. Factors up here with factors down here, eventually. We have to clean this bottom guy up. Okay, we do want to distribute these two factors to these two terms over here. Now, you can actually skip this step here. You can skip this step here if you do the following step, but I will show you this step here to clarify what's going on. And some students might need to do this, especially as they're still learning things or reviewing things. How to work with rational expressions in trig functions, in this case. Now, when we multiply the bottom of this fraction by cotangent of theta, cosecant of theta, what happens? This fraction, 1 over cotangent of theta, gets hit by cotangent of theta, cosecant of theta, plus sign, this carries over. This fraction, 1 over cosecant of theta, 1 over cosecant of theta, also gets multiplied by cotangent of theta, cosecant of theta. Now what happens? We get some cancellations. Cotangent of theta divided by cotangent of theta in red here, these divide out to 1. I should put little ones here, but I'm trying to make things fast. Here, cosecant of theta divided by cosecant of theta is 1. These red pieces basically die out. So then in the bottom, we're left with cosecant of theta plus cotangent of theta. Now again, with time and practice, you may be able to figure that out right from this step here without having to do this step here. So if you do that, great. When you multiply this fraction by all this, the cotangent of thetas die out, they kill each other off, cosecant of theta remains. When this fraction gets hit by cotangent of theta, cosecant of theta, the cosecant of theta pieces die and cotangent of theta remains. So whether you write it all out or you do it more mentally, we end up with this. So we have that product up on top, and we're just left with cosecant of theta plus cotangent of theta down below. And do you see what happens? Do you see what happens? Cosecant of theta plus cotangent of theta is a factor of the entire top. Cosecant of theta plus cotangent of theta is a factor of, in fact, it is the entire denominator. This divided by this is 1. Again, don't worry about hidden restrictions or anything like that. Sorry, I redlined the wrong piece. That stays in black. This piece here goes red. Okay. So cosecant of theta plus cotangent of theta, it's a factor of the entire top and the entire bottom. These divide out to 1s. I should put 1s to indicate what's left. I don't like saying that a denominator just disappears. So we're left with, lo and behold, whoops, we're left with cotangent of theta times cosecant of theta. We're left with this expression in black, cotangent of theta times cosecant of theta. Hey, we hit our target. By the way, if you had switched these, if you had had cosecant of theta, cotangent of theta, then you would have needed one more step. You would have had to switch these factors. Remember, we do want to hit the target, the right-hand side, verbatim, exactly. So your final expression here really needs to match exactly the final expression over here. Give or take parentheses. I know that nowadays I like to put parentheses around the thetas, but don't freak out about that. This is basically verbatim with respect to that. They're copies. So we're done. We've shown that, again, we're not worried about domain issues or hidden restrictions right now. We've shown that the original left-hand side, way up here, is equivalent to this after several steps. And you do have to show basically all these steps, except in the distribution, you can skip from here to here without having to show all of this in gray here. But remember, when you show your steps, you do have to indicate every time you apply a trig identity, for example, showing that tangent of theta is 1 over cotangent of theta. You can do a couple of them at the same time. You can do more than one at the same time, as long as you're working on completely different pieces. Don't do too much blending. Don't do two things on the same part of the expression at the same time. In principle, you could break up more than two of these expressions, working on this, working on this, working on this, and or working on this, provided that you know your places so that you're not doing too much blending or doing more than one thing at once to one part of the expression. But I can show that tangent of theta is the reciprocal of cotangent of theta, and sine of theta is the reciprocal of cosecant of theta in one step. That's okay, because I'm not doing more than one thing on the same piece of the expression. And then when you do a key algebra step, in this case, we're multiplying top and bottom by the overall LCD, then show that. Or show how you're building up these denominators to get a common denominator. Some students may prefer that. Again, you can skip this step if you show this step over here. Show that these two cancel. They divide out to 1. And make sure you get your final expression verbatim. All right. I think that is the best solution. It may be the solution in the book. And then I'll show you my runners-up, my first 3 ways of approaching this. And I think there's a lot to be learned when you stumble along. So I'll show you my 3 other solutions in the notes in the next video.
Any questions? So a lot of the difficulty here was the algebra, right? It was the stuff we did back in chapter 0, how to manipulate rational expressions, LCDs and compound fractions, all that jazz. I noticed that a key strategy, oh yes, let me go back here. Around here, or very last portion, where I kind of around here before you get 1. Yeah, so it's about here, right? So let me go back a little bit. Yeah, I'll start here.
Multiply this fraction by all this. The cotangent of thetas die out. They kill each other off. Cosecant of theta remains. When this fraction gets hit by cotangent of theta, cosecant of theta, The cosecant of theta pieces die, and cotangent of theta remains. So whether you write it all out or you do it more mentally, we end up with this. So we have that product up on top, and we're just left with cosecant of theta plus cotangent of theta down below. And do you see what happens? Do you see what happens? Cosecant of theta plus cotangent of theta is a factor of the entire top. Cosecant of theta plus cotangent of theta is a factor of, in fact, it is the entire denominator. This divided by this is 1.
Okay. So that's the key insight there. Any questions up to that point? Any questions up to that point? Let me know if you have questions. I'll continue on. I know a lot of people need this.
Again, don't worry about hidden restrictions or anything like that.
Yeah, I redlined the wrong piece.
Sorry, I redlined the wrong piece. That stays in black. This piece here goes red. Okay. So cosecant of theta plus cotangent of theta, it's a factor of the entire top and the entire bottom. These divide out to 1s. I should put 1s to indicate what's left. I don't like saying that a denominator just disappears. So we're left with, lo and behold, whoops, we're left with cotangent of theta times cosecant of theta.
So that basically ends my verification. But I was making the point that if you had switched these two, you have to switch them. We have to switch them to the right order because technically you're supposed to hit the target verbatim, right? So if you got cosecant of theta, cotangent of theta, switch the factors, make sure you get this, right? Any questions? Any questions? Because this was an involved one, right? Any questions? Actually, keep thinking about this. It's a good time to do one of my videos. Actually, this is one of my favorite ones. So, folks, you're often going to feel frustrated because you're not hitting your target, right? You're not getting what you want. So here's Homer missing his target. I really like this video. It's very appropriate. All right. Okay. Any questions? By the way, any further questions here? Any questions? All right. Let's continue. I'm going to show you my runners up for solutions.
And then I'll show you my runners up, my first 3 ways of approaching this. And I think there's a lot to be learned when you stumble along. So I'll show you my 3 other solutions in the notes in the next video.
Okay, concisely. I don't want to waste your time.
Hi, everyone. We're continuing with verifying trig identities. In my previous video, I showed what I thought was a superior solution for verifying this trig identity. I'm going to show you 3 other solutions I used before I got to my best solution. And as I stumbled along, I learned a lot. And I think students learn a lot as they stumble along and they try different strategies. You're not going to come up with the best strategy right off the bat all the time. So it helps, first of all, to take a step back and think and strategize, because it may be to your benefit to think and strategize. My most clever strategy, internal consistency, which I applied in the last video, led to far fewer steps than what I ended up with for these other solutions over here, among these first 3 I tried out. So it's often smartest to take a step back and think, what can really work to get me from the left-hand side in this case to my target, the right-hand side here, in the fewest steps, in a way that's easily explainable. All right. Now, for my 3 inferior solutions, but still, these are very educational, and you'll learn a lot in terms of the various trig and algebraic strategies you can apply. All right. Oh, and by the way, I like putting parentheses now around my arguments, but if your argument is just theta, it's not a problem. Okay. Method 1. A student often looks at something like this and goes, oh boy, I see cosecant, cotangent, tangent. Let's break everything down into sine and cosine of theta. And that was my very first strategy, to break everything down to sine and cosine of theta, using the reciprocal and quotient identities. So my method 1. I start at the left-hand side. Here I copied the left-hand side, but you could write LHS instead of copying the left-hand side. but you better indicate which side you're starting at. Again, let's apply the reciprocal and quotient identities to break these things down into pennies and nickels, sine of theta and cosine of theta. All right, cosecant of theta by a reciprocal identity becomes 1 over sine of theta. Cotangent of theta by a quotient identity becomes cosine of theta over sine of theta. Tangent of theta by another quotient identity goes to sine of theta over cosine of theta. Sine of theta is already pretty nice, but it might actually help if we put it over 1, since it's clear that we're going to have to manipulate fractions. That may be a helpful thing to keep in mind. Now, it's okay to apply these 3 identities all at once, simultaneously, because I'm working on different pieces of the expression. I'm not doing 2 things on the same thing, on the same part of the expression. Otherwise, you should separate your steps. But here, this goes to this, right? Upper left goes to upper left, upper right goes to upper right, lower left goes to lower left. The lower right basically stays the same, or you put it over 1. So in a case like this, you can do this all in 1 step, even though you're technically applying 3 identities at once. Again, you want to separate steps if you're doing more than 1 thing on 1 part of the problem, the expression. All right. Now, on the top, we have a common denominator, so we can add those fractions, those rational expressions. So we have on top the fraction 1 plus cosine of theta over sine of theta, and on the bottom, we have this sum of fractions. Now, we could try to get a common denominator down here so that this new denominator down here becomes cosine of theta. To accomplish that, I multiply this fraction. That's one reason why I put sine of theta over 1, so I get a fraction here. It may make things clearer. Let's multiply this fraction by 1 by cosine of theta over itself. So I'm basically multiplying that bottom right fraction by 1. And then I eventually get a common denominator in the bottom here. So again, I multiply sine of theta over 1 by cosine of theta over cosine of theta. It's much more nicely typed over here. I get a common denominator down below. Add the fractions, and now I get this compound fraction, but at least I have 1 fraction divided by another fraction. When we divide by any non-zero quantity, say a fraction, we multiply by its what? We multiply by its reciprocal. We multiply by its reciprocal. But do separate the steps. So don't do any multiplication just yet. Do it in the next step. When we divide by a non-zero quantity, we're multiplying by its reciprocal. So I'm flipping the top and the bottom here to get this. Now, what can I do with this ugly piece in the lower right? We can factor out sine of theta. You could do a snap substitution. You're basically following this template. You're factoring x plus xy, basically, where x is sine of theta, y is cosine of theta. Basically, you can factor out an x or a sine of theta. When we do that, we get sine of theta times the quantity 1 plus cosine of theta. And we are allowed to cross-cancel, cross-divide. Because in the end, when we multiply fractions, we multiply across. We can divide the 1 plus cosine of theta up in the upper left by the 1 plus cosine of theta in the bottom right. Their quotient is 1. Again, we're not worried about domain restrictions right now. Because we could do that even if we had eliminated the little dot here and made this a straight fraction with grouping symbols there. Boom, boom. All right, so these go bye-bye. And we are left with cosine of theta over sine squared theta, basically. But actually, I'm going to leave it peeled apart like that. I like these separated. Because what's the target? It's going to keep the target in mind. What's the target? The target is this. Cotangent of theta cosecant of theta. That's our target. And this is looking pretty close. What is 1 over sine of theta? It is cosecant of theta. And what is cosine of theta over sine of theta? It is cotangent of theta. Now, is this our target? Not quite. Our target is officially cotangent of theta times cosecant of theta. So let's switch these factors so that we get the right-hand side verbatim. Cotangent of theta, cosecant of theta. We can put parens. All right. So that took some clever algebra along the way. We do have an appropriate solution, though, although you can see it took longer than the internal strategy session I did before. That's strategy. Okay, we'll look at some more strategies and solutions in the next video.
Yeah. So I understand that was a lot of writing, and after the end of the videos, if you want me to go back and review this, that's fine. Because many students start with, boom, sine and cosine, right? Breaking things apart. The algebra is a bit more complicated, though, as you've seen. Okay. Yeah, in a situation like this, you might want to listen and try to absorb things more so than speed writing. Remember, the notes are online. Any questions before we go on to... Now, again, I'm going to kind of skim over these, right, where you kind of look at the variations. I realize that if you're writing, you might want to wait until you look at my notes later on.
Hi, everyone. I don't want to bore you to tears, but I want to quickly discuss 2 more methods for attacking this identity and verifying it. Now, actually, what if we start off with the way we started off method 1 and broke this down to sine and cosine? Once again, this is the same as for method 1. But this time, we're going to do the algebra differently. This time, instead of getting a common denominator in the top and the bottom, we're going to use our trick from method 4. So I'm kind of fusing together methods 1 and 4. I'm multiplying the top and the bottom by the overall LCD, which is the product of sine of theta and cosine of theta. So I multiply by this over itself. Overall, I'm multiplying by 1. Now, in method 4, I had something very nice in the upper left, so I did not have to distribute up on top. This time, I have fractions inside both the top and the bottom of the overall fraction. So I do want to distribute these guys through both the top and the bottom. You can either show it, or you can skip this step and try to do it mentally. With time, you can do this mentally, but be careful. The survivors, after you distribute on the top and the bottom, end up giving you this. Cosine of theta plus cosine squared of theta over sine squared of theta plus sine squared of theta cosine of theta. On both the top and the bottom, what can you do? Hint, a substitution might help. What could you do with x plus x squared, for example, up on top, and y squared plus y squared x on the bottom? You can factor. And in fact, this snap substitution could help you. You might want to show this or not. But anyway, when you factor, hey, look at this. On both the top and the bottom, you get 1 plus cosine of theta. As factors of the entire top and the entire bottom, they divide out to 1. Again, we're not worried about hidden restrictions. You end up with cosine of theta over sine squared of theta. But now, wait a minute. When you look at the target, I don't see any squares here. I see cotangent of theta times cosecant of theta. So I'm going to peel this thing apart. It's like factoring. I'm going to tear this apart. I'm going to peel it apart. Well, sine squared of theta is just sine of theta times sine of theta, right? Kind of like this rule. So I'll write this as cosine of theta over sine of theta times 1 over sine of theta. There's a 1 on top here. And then from quotient and reciprocal identities, we get cotangent of theta, cosecant of theta, okay, which is what I want. Bear in mind, if you had torn this apart in a different order, if you had put this guy in front, you would eventually have to switch and get to here. But that's fine. Multiplication is commutative. You can switch the order. All right. So that was my method 2. in my evolution, in method 3, I got smarter. I used the idea of internal consistency. Remember that? I used that in method 4. So I used the key strategy from method 4. But the thing was, I made cosecant of theta look like sine of theta. I made cotangent of theta look like tangent of theta. I used the reciprocal identities this way, which seems very natural to students, and it did to me. The thing was, I was going the wrong way because I forgot about the target. Remember, method 4, the better method, I applied a similar strategy, but I got really smart. I made the pieces look like cotangent of theta and cosecant of theta. Here I went the wrong way. I made these guys look like these guys, which I think we're inclined to do early on because we're just more comfortable with these two functions of theta. But anyway, it does work. It takes some more steps. So I built up these two fractions to get a common denominator up there. Or you could multiply through by the LCD, sine of theta times tangent of theta, like I did in method 4. This is over 1. Remember, when you divide by something non-zero, you're multiplying by its reciprocal. Basically, you do get a cancellation here. These do divide out to 1, but that may not be entirely clear. It may be easier to think of this as multiplying by the reciprocal of that. Then you see these guys cancel out. 1 over sine of theta tangent of theta. Let's peel it apart, factor it. 1 over sine of theta times 1 over tangent of theta. That gives us cosecant of theta times cotangent of theta. But we want it verbatim. To the right-hand side. We switch factors and get that. So 4 ways. Pick your poison, 4 ways. I would accept any of these on homework or exams, but strategizing helps. I think method 4 was by far the best solution. It was the most concise and shortest solution, and it helped that I strategized first, using ideas of internal consistency and aiming for the target. So strategizing helps. I'm going to discuss some more strategies and list them out in later videos.
So again, I need a balance because any questions? I want a balance between not boring you, right? But so I want to go through the various steps here. For those of you who are interested, if you want to take the time after class, either today or some other day, I'd be happy to go over and review some of these. But I want to skim over some of these variations so that you see some of the algebra that might come into play. I realize that I'm really throwing floods at you. So if you want to see these discussed in greater detail, I can do that with you after class. Okay, any questions? We're going to summarize some strategies. Although I think this one, we still have this one to do, right?
Hi, everyone. We're continuing with 5.2, and I want to show you another strategy which is used in calculus proofs. It involves what I call trig conjugates. Now, back in your Algebra 2 class, you saw expressions like these, 1 over root 3 plus root 5, and you wanted to rationalize the denominator. Well, how did you do that? Well, you multiply this fraction by the conjugate of the denominator, root 3 minus root 5. And you multiplied that on the top and on the bottom. And why did you do that? Because you're using this basic algebra rule, which says that when you're multiplying a plus b and a minus b, the result is a squared minus b squared. So when you multiply a sum times a difference of the same two things, you have a squaring effect. Now, why do we want the squaring effect over here? Well, what's the square of the square root of 3? It's 3. And similarly, the square of root 5 is 5. So when you multiply these two bottoms together, you get 3 minus 5, or negative 2. And you get rid of those radical signs, in the bottom at least. So you end up rationalizing the denominator. Now let's say you have something like this. 1 over 3 plus 2i. We don't like the fact that the denominator is imaginary. So we multiply by, this time, the complex conjugate of the denominator on the top and the bottom. 3 minus 2i over itself, 3 minus 2i. And the reason is, again, because of this rule over here. And ultimately, it's because I squared is what? I squared is -1. And we end up, quote unquote, realizing the denominator. In particular, when we multiply these two bottoms together, 3 squared is 9, minus the square of 2i is 4i squared. So then we have 9. Okay, now -4i squared, that's -4 times -1, that flips over to a +4. And then 9 plus 4 ends up being 13. That's our new denominator, with this guy here as our numerator. So this idea of multiplying a sum or a difference by the corresponding difference or sum, we're exploiting this algebra rule here. Now, what about trig conjugates? Why do we like squares of trig functions? Because we can often use what kinds of identities if we're dealing with squares of trig functions? The Pythagorean identities. And again, this is a key reason why we see these a lot in calculus proofs. They often involve Pythagorean identities. So for example, let's verify that this left-hand side is equivalent to this right-hand side. Well, let's see. Secant of alpha minus tangent of alpha. I guess I could break these guys apart into fractions, but let's take a chance. Now, there is a risk to using trig conjugates. You're in danger of making something more complicated. But here, I think we're going to be fortunate. Because what is the trig conjugate of secant of alpha minus tangent of alpha? It's actually this guy, secant of alpha plus tangent of alpha. So it looks pretty fortuitous. Let's take the left-hand side. We multiply by 1 in the form of secant of alpha plus tangent of alpha, the trig conjugate of the bottom here, over itself. On the top, we get secant of alpha plus tangent of alpha. And on the bottom, because of this rule again, we get secant squared of alpha minus tangent squared of alpha. Now, if you're keeping your eye on the target is secant of alpha plus tangent of alpha, the numerator of what we have right now. So you're really, really hoping that this bottom is what? You're really hoping this bottom is 1. And that could be the case because these do form a pair of squared trig functions that we see in the Pythagorean identities. And the result could be 1. And in fact, this is equivalent to 1. Ignore domain problems for right now. Let's verify that. Now, you may know the key trig identity, Pythagorean identity we're going to use here in this form with alpha. Tangent squared of alpha plus 1 equals secant squared of alpha. Well, how can you get this, isolate this on one side? By subtracting tangent squared of alpha on both sides, and you end up with this, which basically tells us that we can replace secant squared of alpha minus tangent squared of alpha. We can substitute that with 1. Again, we're ignoring domain restrictions and domain problems for now. Also, keep in mind, if we had a plus sign down there, we could try applying Pythagorean identities, but we would get things that are much more complicated than 1. If we had a plus sign here, I don't think a Pythagorean identity would help us much. But with a minus sign, great, this is 1. And in fact, we end up with the right-hand side we wanted, secant of alpha plus tangent of alpha. If you really want to end this verification, you could say something like QED, remember, which is Latin for end of proof, basically. But I won't require that. We end up with the right-hand side. Now, a more controversial solution, some people might look at this and go, well, why don't I just try multiplying both sides by the bottom here? Well, then the idea is that you're writing equivalent equations. And again, you're keeping domain issues on the side. The idea is that you're trying to write down equivalent equations. So if you do that, if you multiply both sides by that, You end up with this, and the right-hand side becomes that by the algebra rule. You could add tangent squared alpha to both sides to make it clearer that, yes, we do end up with a known Pythagorean identity. You could go even further and say, hey, tangent squared of alpha plus 1 is secant squared of alpha, and that's equal to itself. So here, you'd be using the logic of, well, the original equation, if you think of this as an equation, is equivalent to this equation over here, which we know to be true, as long as there's not a domain problem. Will instructors accept this? It depends. Some instructors may not like this very much, so you might be safer and better off doing what we usually do. Start on one side and end at the other side, just to be safe. All right. Next, we're going to summarize our various strategies next time.
All right. Any questions? Any questions? Don't go too nuts with the trig conjugates thing, because sometimes you make it worse. You make things worse. So it's in specific cases where it can help, though. Right? Questions? So we'll do let's do the summary. Well, let's see. Yeah, let's go and do the summary, and then we'll take a break.
Hi, everyone. Let's conclude section 5.2 with strategies or toolbox tools that will help you in both 5.1 and 5.2 when you simplify trig expressions and verify trig identities, which can be thought of as harder simplification problems with harder expressions where you're given the answer. Okay, so a summary of strategies. This is not a comprehensive list, but it's a good toolbox. So for a verification problem, you usually start with the larger, longer, more complicated side and trash compact it down to the shorter, smaller side. That's usually the way it goes. Although, sometimes you do go from smaller to larger. For example, with the trig conjugate trick we'll discuss later on, that sometimes happens. But that is a last resort, though. It's usually easier to shrink something than to blow it up. Aim for the target. So let's say that you start at the left-hand side, target and aim for the right-hand side. That would have made my first problem a lot easier. That was my solution 4, which I presented first. Aim for the target. If your target has cosecant and cotangent, try to get cosecant and cotangent in your expression as soon as possible. Third, be prepared to apply the fundamental identities. You probably will have to. So keep them in mind. Reciprocal, well, let's review them, right? In order, probably reciprocal, quotient, then probably Pythagorean. Even, odd, or negative angle, and the cofunction identities. So these 5 categories. And be prepared to apply them step by step and carefully. It's okay to work on different pieces of the same expression, but don't do too many steps. Don't do too many things on one piece, one part of the expression. Then you want to separate your steps. When working with fractions, especially when you're adding and subtracting fractions, be prepared to use LCDs, least or lowest common denominators. They also help when you're simplifying compound fractions, like blah, blah, blah plus blah, blah, blah over blah, blah, blah plus blah, 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 or maybe with minus signs. Trig conjugates. Because squares of trig functions can help you apply Pythagorean identities. It's usually helpful if you have partners in the same Pythagorean identity in a given expression. For example, sine and cosine, or tangent and secant, or cotangent and cosecant. Maybe 1 or -1 might be involved as well. But in a way, it's kind of a last resort as a strategy, because you tend to make the expression more complicated, and students might overuse the strategy on exams, actually. So think about it, look at the expression, and see if a Pythagorean identity might eventually be appropriate. Again, these pairs of trig functions might be signals. or maybe a 1 or a negative 1. Okay, and then we have more algebraic strategies, like decomposition strategies, breaking things apart, going to sine and cosine, breaking things down to pennies and nickels, and then trying to construct something from out of that. Keep the target in mind. Now, that might be a good all-purpose brute force strategy, but it may not lead to the most efficient strategy, as we saw in my first example for this section.
By the way, I know an editor got on my case for this. If you're writing professionally, you're supposed to write out sine, S-I-N-E, and cosine, C-O-S-I-N-E. So these are notes where I'm using the shorthands.
Factoring. Factoring is still legal. Keep that in mind. You might want to do snap substitutions or actually write them out. Actually write out stuff like x squared plus x squared y squared and see what factors out. Okay, so do a snap or explicit substitution and factor. Splitting a fraction. If you're doing it in the context of multiplication and division, we're thinking in terms of factoring or peeling. For example, and you do this a lot in calculus, cosine of theta over sine squared theta can be written as cosine of theta over sine of theta times 1 over sine of theta, where you're breaking apart the bottom. You could, of course, reverse the order. Again, keep the target in mind. You can also split a fraction through the numerator if you have addition or subtraction. For example, remember this kind of rule. You can break a fraction through the primary plus and or minus signs in the numerator. That could help. So if your target has more than one term, that's a strategy you might want to apply. Keep the target in mind. Remember, though, that we do not split through the denominator. For example, if you see something of the form 1 over x plus y, I would not recommend a splitting strategy. Some other strategies. The idea of a template. And I did this back when I discussed factoring, right? A template, like factoring, for example. How do you factor something like this? How do you factor a x squared plus y squared? Things like snap substitutions. Be prepared to look at a similar problem in Algebra 1, like a template. That could help with factoring, when you're manipulating fractions, and so forth. In general, be neat, show work, show things step by step, and don't apply more than one identity to the same part of an expression unless you separate out the steps first. Don't do too much on one piece of the expression. Otherwise, you have to separate your steps. Make it clear when you're applying each fundamental identity, so you're not smushing things together. And also overall algebraic strategies, like multiplying by something over something, like a trig conjugate. Or if you're in the process of simplifying a compound fraction, and you're using, say, an LCD. And strategy number 12, which I discussed in my best solution for the first problem in this section, internal consistency, making pieces look like each other, and also aim for the target. That's also a good combination rule. Internal consistency and aiming for the target, which helped us a lot in my solution 4, which was the first solution I presented for that first verification problem in 5.2. Okay, next up, we're going to solve trig equations, 5.3.
No, next up is a break. Okay, so long overdue. We're done with 5.2 with that. Okay, I have 8:25. So I will see you at 8:37. Let's say 8:37 actually. 8:37 p.m. Okay, remember to mute. Okay, we've had some incidents both locally and nationally where people should be muting audio, video, whatever. All right, and I'll record later. Please mute. All right. Okay, so the videos will end about 9:09 today. Okay, now the chapter 4 problems tend to be short. Even the graphing ones I can explain pretty quickly. They can be tricky, okay, but they tend to be short, right? They're not like monsters. And of course, I'm willing to go past 9:30 if necessary, but the videos will end about 9:09. Okay, any general questions before we go on? Any general questions? And you know how attendance works, right? It's not that I take attendance. It's more that I track who's chatting, for example. And of course, the videos help a lot. All right, that's good to have my commentary. All right, any questions? Any questions? All right, so let's restart. Okay, we are recording.
Hi, everyone.
Oh, and by the way, this stuff will help you on the chapter 4 homework. All right, like 4.7. This stuff will help on chapter 4.
Let's start section 5.3 on solving trig equations. We did a bit of this back in 4.7. Let's do more of this more systematically. First of all, we're going to look at basic equations in sine, cosine, cosecant, or secant. Notice my two exceptions, tangent and cotangent, and think about how they're different, by the way. How are tangent and cotangent different from these other guys? And we're going to consider linear forms in these trig functions, linear forms. Meaning, if you do a substitution, you basically get a linear equation. For example, here, well, if we try to solve this equation, 5 cosine of x minus root 2 equals 3 cosine of x. Well, you might want to apply the substitution. You don't have to, but you can apply the substitution u equals cosine of x and start by solving this linear equation, 5u minus root 2 equals 3u. Solve this for u. In fact, let's go ahead and do that. 5u minus root 2 equals 3u. Let's start by adding 2 to both sides.
Yeah, adding root 2 to both sides. Remember, check my my description of the video because I have corrections there. Add root 2 to both sides.
So we add 2 to both sides. Don't say move, say add. Add root 2 to both sides. Subtract 3u from both sides. 5u minus 3u is 2u. To isolate u, divide both sides by 2. U equals root 2 over 2. And then sub back, u is cosine of x. Cosine of x equals root 2 over 2. Now, you did not have to do a substitution. You could have just left this in cosine of x. Many students do. So again, add root 2 to both sides, divide by 2. In either case, whether you use a substitution or not, we get cosine of x equals root 2 over 2. And we basically solved a linear form for u or cosine of x. So we started off with some basic algebra. And now we look at cosine of x equals root 2 over 2, and we might think, oh, piece of cake. Well, take a step back and think. It's easy to write down something wrong here. This looks deceptively easy. We want to solve this equation, and the assumption is that we solve it on R. We want all real solutions for this equation, and therefore all real solutions for this equivalent equation over here. We want all real solutions. That's the assumption, unless you're told otherwise. Find all real solutions. That is assumed unless otherwise stated. So first of all, if you consider x as an angle, that might be a bit confusing. But if you consider x as an angle and you consider the unit circle, the way that some instructors do it, they would put cosine of x on the horizontal axis and sine of x on the vertical axis. Okay, because it can be a bit confusing. It is true that cosine of x is like an angle here. Cosine of x is like the x coordinate on the unit circle. It's the horizontal coordinate. Okay, so we want to know in what two quadrants is cosine of x positive? First of all, actually, you should agree that root 2 over 2 is a legitimate cosine value. It's between -1 and +1. So this is a legitimate cosine value. And in fact, It's a well-known cosine value. It's a famous one. Root 2 over 2 is a famous one. But once again, in what two quadrants is cosine positive? Remember, cosine of x is the horizontal coordinate. I don't quite want to say x coordinate. It's the horizontal coordinate on the unit circle. X is technically the angle here. Well, cosine is positive in quadrants 1, put that in blue. Blue, right? And quadrant, what else? Quadrant 4. Quadrant 4. The horizontal coordinate. Okay. We used to think of it as the x coordinate. Here, x is technically the angle, though. But in quadrants 1 and 4, cosine is positive. All right. Well, it helps to find the reference angle for the solutions. And in fact, the reference angle turns out to be a solution itself. What's the inverse cosine of root 2 over 2? What is the famous acute angle, quadrant 1 angle, whose cosine value is root 2 over 2? It is pi over 4. So let's start with that, with pi over 4. This northeast point, we know that pi over 4 is in fact the reference angle, actually, for all the solutions. In what other quadrant is cosine positive? Quadrant 4. So we're also interested in this point over here. And what angles could we associate with this point? Well, there is 7 pi over 4, but since we want all real solutions, do you know what an easier representative for this point would be? By representative, I mean any coterminal angle that would correspond to this point over here. You can pick any one. Which of those representatives for this point would you pick? What's even easier than 7 pi over 4? How about negative pi over 4? We want all real solutions anyway. It turns out this makes things convenient for us. So what is our solution set for this equation? Cosine of x equals root 2 over 2. I want any representative for this point over here and all its coterminal twins, basically all the representative angles for this point. And I want all the representatives for this point. So I pick one representative, and then I take all of its coterminal angles. So very simply, by the way, remember these points here correspond to a horizontal coordinate of root 2 over 2. Remember the horizontal coordinate is cosine of x, the cosine value of the angle. Easy way to write the solution over here. The set of all x in the reals, I like to put that nowadays, the set of all x in the reals, sneaking that in there, such that x is of the form plus or minus pi over 4 plus 2 pi n, where n is integer. Here's the shorthand for that, where n is in the set Z. And we want both the plus and minus signs in there. And that would be an appropriate solution set. It has infinitely many solutions corresponding to the infinitely many angles that correspond to both this point and to this point, including pi over 4 and its coterminal twins, and negative pi over 4 and its coterminal twins, including 7 pi over 4. Now, if you really like positive angles, or if you're going to do a multiple angle type problem, like we're going to see later on, you might prefer the 7 pi over 4. That's okay. You could just as well write the solution set as follows. I will accept any solution set that's correct, within reason. The set of all x in the reals such that x is of the form pi over 4 plus 2 pi n, where n is integer. Again, that can be written like this. That takes care of all the representatives for this northeastern point over here in quadrant 1. or of the form x equals 7 pi over 4 plus 2 pi n, where n is integer. That gives us all the representatives for this southeastern quadrant 4 point over here. I'll accept either the solution set in red or in blue. In fact, you can take any representative, any coterminal angle for pi over 4 over here, and any representative for this point in the southeast, or any coterminal angle for 7 pi over 4 over here. For that matter, you can switch these two guys. As long as your solution set is correct and reasonable, I'll accept it. Although books try to aim for the most compact and efficient form possible. Bear in mind, I needed the plus or minus in front of the pi over 4 here, unless I was going to write out different angles like 7 pi over 4 over here. So I needed the plus or minus here if I wasn't doing something like that. But I don't need a plus or minus here because remember, n could be a negative integer. N could be -1, -2, or so forth. So if you were to put a plus or minus sign here, that would not be wrong, but it would be redundant or superfluous. N can be negative. So we leave it as plus 2 pi n. That's how we get all possible coterminal angles, by putting plus 2 pi n where n is integer. We go around an integer number of revolutions, either counterclockwise or clockwise. So that was our first solve a trig equation problem in this section. Remember, your answer to a solve an equation problem is a solution set. Now, actually, there is a way of visualizing this. And I'll discuss that briefly next time.
Okay, any questions? Any questions? I'm gonna go to Desmos and show you what's up with this graphically. Any questions? Any questions? Solving trig equations. These ideas will help you in 4.7 also.
Hi, everyone. We're going back to the first example in section 5.3, where we're solving this trig equation on the reals. We want all real solutions for this equation. Now, as a first step, we ultimately isolated cosine of x. You might want to substitute in the meantime. Let u be cosine of x, solve for u. But basically, we got this equivalent equation. And instead of solving the original equation, it's a lot easier to solve this bottom equivalent equation over here. Cosine of x equals root 2 over 2. We found the solution set for this equation. And there are different ways of writing it. But basically, they corresponded to all the representatives for this northeastern point in quadrant 1 and this southeastern point in quadrant 4. All the representatives for this point, that is pi over 4 and all its coterminal twins. Also, this point over here, one representative is 7 pi over 4, or more conveniently, negative pi over 4, and also its coterminal twins. So all the representatives for that point. So there are at least a couple of different ways. In fact, there are infinitely many ways of writing the solution set well. Let's talk about some graphical implications. Again, we're solving the equation. Well, after our algebraic manipulations, we're solving the equation cosine of x equals root 2 over 2. And we want to know the real values of x that will make this equation true. In a way, we're solving the following system for x. We're solving the system, we'll talk more about systems later, but we're solving the system y equals cosine of x and y equals root 2 over 2. We're solving this system for x. Solve this system for x. And the y-coordinate is going to be root 2 over 2. The solutions for the system will correspond to intersection points between the two graphs. Where are the values of x that will make cosine of x equal root 2 over 2? And the y-coordinate will be root 2 over 2 at those intersection points between these two graphs. So the solution set for this equation consists of infinitely many solutions, real values of x, that correspond to where cosine of x is equal to root 2 over 2. the x-coordinates of the intersection points between these two graphs. Well, how do we graph? Y equals cosine of x is this cosine wave. Remember, it starts at a max point at x equals 0. It's also an even function, symmetric about the y-axis. If we graph y equals root 2 over 2, we get this horizontal line representing a constant function. And again, all the solutions for that equation, cosine of x equals root 2 over 2, will correspond to intersection points between these two graphs. All the points where both the red and the blue graph have y-coordinate root 2 over 2, which is about 0.7. Let's point at this point over here. Pi over 4, comma, the 0.707 is a rounding off of root 2 over 2. Likewise, over here, 7 pi over 4, comma, basically root 2 over 2. Remember, pi over 4, 7 pi over 4. Those corresponded to two solutions in our solution set. Where else did we get solutions? For what other x-coordinates? Well, I guess you can't keep points labeled if you slide things, but here we have pi over 4, comma, root 2 over 2. Guess what? Here's negative pi over 4, comma, root 2 over 2. Negative pi over 4 was also a solution. Remember, it corresponded to the southeastern point in quadrant 4 as well. So the representatives for this northeastern point in quadrant 1, pi over 4 and its coterminal twins. We have pi over 4. We also had these other points on the downswing, 9 pi over 4, that's on the downswing. Also over here, 17 pi over 4. Notice we have here pi over 4, and then if you add 2 pi, you get 9 pi over 4. You get that point, intersection point between the red and the blue graphs. Also at 17 pi over 4, and so forth. Oops. What about on the upswing? When this graph is going up, we had negative pi over 4, comma, root 2 over 2. Also, remember, 7 pi over 4, comma, root 2 over 2. That's if you add 2 pi to negative pi over 4. If you add another 2 pi, you get 15 pi over 4 over here. Or you could go to the left. Negative pi over 4 minus 2 pi gets us negative 9 pi over 4, corresponding to this intersection point here. So we can look at things graphically. Again, the solutions to the equation cosine of x equals root 2 over 2. The solutions to this equation are given by the x-coordinates of the intersection points between the two corresponding graphs here. Y equals cosine of x and y equals root 2 over 2. By the way, what if we just wanted the solutions between 0 and 2 pi? If we go around the world, we just have two solutions. The pi over 4, which I will put in blue over here, pi over 4, and also what? Also, not negative pi over 4, 7 pi over 4, and that's it. Between 0 and 2 pi, we only pick up two non-negative solutions, pi over 4 and 7 pi over 4. So if I had asked you to solve that equation, either this one or the original one we had, if I had asked you to solve it only on the interval from 0 to 2 pi, then this would have been your solution set. It would have had exactly two solutions corresponding to the pi over 4 over here and the 7 pi over 4 over here, because we're only allowing solutions between 0 and 2 pi for x. Next up, we'll solve for more trig equations.
Any questions? Play with Desmos. They'll help enhance your intuition. We have one final part next. One comment. I want to show you, just to remind you, when you start a video, look at the descriptions and see, I have corrections here. Like about 11 minutes in, I'm gonna have to remind myself, N in Z, not R. So that's a correction I have. So every time you start a video, look for corrections. Okay, because it's very time consuming, or it would bloat my video to make edits. If I try to edit these videos, it bloats the memory by a factor of 5. It's not worth it.
Hi everyone, let's continue with section 5.3 on solving trig equations, linear forms, where we don't have any squares or other powers on the trig functions. So let's solve secant of x minus root 2 equals 0. For a linear form, you generally want to isolate the trig function on one side. Let's add root 2 to both sides, and we get secant of x equals root 2. Now, you are allowed to take the reciprocal of both sides as long as they're not 0 and they're defined. Well, root 2 is a nice defined non-zero number. We can take the reciprocal of both sides. Be careful about doing this if you have more than one term on one side. But we have one term on the left, one term on the right. We can take the reciprocal of both sides. We get cosine of x equals 1 over root 2, or when we rationalize the denominator, root 2 over 2. And then you see I'm playing a trick on you. Cosine of x equals basically root 2 over 2. That's the same equation that we solved earlier. Really, we had a more complicated equation earlier, but it boiled down to this. So you have the same solution set. I'm playing games with you here. It's the same solution set. How about this here, though? Sine of x equals 2. In a way, that's another trick question. What's the solution set for that? Sine of x equals 2. What real values of x, what angles have the property that the sine of that angle equals 2? Empty set is the solution set. Because no real values will work here. 2 is not in the what of the sine function. 2 is not in the range of the sine function. So there are no real solutions for x. The solution set is the empty set. Next up, let's consider linear forms in tangent and cotangent. And why were these two different? What made tangent and cotangent different from the other trig functions, aside from their graphs, really? It was their period. So we tend to get more symmetry when we deal with equations with tangent and or cotangent. We're going to see that. For example, let's solve the equation tangent of x equals negative root 3. Now, is negative root 3 a tangent value? Is it in the range of tangent? Remember, tangent is very liberal. Tangent is slope. Any real number can be a slope, even positive 1 million, even negative 1 million. Any real number can be a slope, including negative root 3. And you might recognize that negative root 3 is a famous tangent value anyway. But here's the problem, though. We're more familiar with the case where tangent of x is positive root 3. So instead of finding the solutions to this right off the bat, let's find the reference angle for all the solutions. Find the reference angle for all the solutions. So I'd like to know where tangent of x is equal to positive root 3. Where's tangent of x equal to positive root 3? For some acute angle x. For some acute angle x. In other words, what's the inverse tangent of root 3? Well, let's see. Tangent is slope. Root 3 is about 1.7. That's a famous slope. It's pretty steep. What's the corresponding angle? Pi over 3. Which was 60 degrees, by the way. Pi over 3 radians. Now, is that going to be a solution for our equation? No, because tangent of pi over 3 is positive root 3. So pi over 3 itself is not a solution. It's not itself a solution. Too much blue here. Let's go ahead and make this red. Or whatever that is, purple, not itself a solution, but it's the reference angle for all of our solutions. So it comes in very handy. It's the key brother for all the solutions, and that's going to help a lot. All of our solutions will have pi over 3 as the reference angle. That's really helpful. So now, in what two quadrants is the tangent value negative? In what two quadrants is the tangent value negative? Again, tangent is slope. Think of a decreasing line going through the origin. Tangent is negative in quadrants 2 and 4. In these two quadrants, tangent is negative. So this is very nice. I want all the angles with reference angle pi over 3 that lie in quadrants 2 or 4. I'm really in business. Who are they? Again, who are they? Think about it. Who are the brothers of pi over 3 in quadrants 2 and 4? Think of some famous ones. Actually, notice this. If you use symmetry, rotational symmetry, you only need to identify one brother. Let's go back to this unit circle. Where are the points I'm looking for? I'm looking for the point here. I want all the representatives for this point. And I want all the representatives for this point. I can take any of the representatives for either of these points. Basically, I can take any representative for any of these 2 points and go from there. I only have to identify one solution angle. The easiest one might be negative pi over 3. Although a good angle for this point here is 2 pi over 3, you could also pick that. But I don't need both. In terms of stating my solution set, I only have to identify one of them. I only need one representative for one of these points. Let's say negative pi over 3. And why is that the only angle I need to identify? I just have to identify one angle. So the solutions to the equation, tangent of x equals negative root 3, will correspond to this point and this point. Basically, the solution set consists of all the representatives for this point and all the representatives for this point. But here's how I can get them. I start with any representative for either of these 2 points. Let's say the negative pi over 3. I start with negative pi over 3. What can I add to get the 2 pi over 3 over here? Well, I'm rotating by half of a revolution counterclockwise. I can add pi to get to this point over here, and I get 2 pi over 3. And then I can add another pi. That is, I can add 2 pi total to get a coterminal angle over here. Add 3 pi, I'm back here. Add 4 pi, I'm here. Add 5 pi, here. Add 6 pi, here, and so forth. I can also subtract pi. If I take negative pi over 3 and I subtract pi, I'll get a coterminal angle for this, namely negative 4 pi over 3. Notice that if you had chosen 2 pi over 3 as the angle to focus on, if you subtract pi, you would have gotten negative pi over 3. So basically, I can take any representative for either point and I add any integer multiple of pi, where n is any integer. Now, here's a simpler way to do it, although it takes more writing. I would accept this. You could say that the solution set is the set of all x in the reals such that x equals negative pi over 3 plus 2 pi n. So you grab a representative for this point and take all coterminal twins, or x equals 2 pi over 3 plus 2 pi n. So you grab a representative for this point and take all coterminal twins, where n is integer. I would accept that, but that's more writing than you need, as I just observed. You could just say that the solution set is this or this, the set of all x in the reals I'll write this better. It's technically optional, but it's good to write. The set of all x in the reals such that x is of the form, well, you could take the negative pi over 3 or the 2 pi over 3. You could take a rep for this point or a rep for this point. Plus pi n, where n is integer. So again, how can you sweep over all of the solutions in the solution set?
Remember my correction. That's not an R. It's a Z. So watch my corrections. That's a Z.
Take any representative for either point, say the negative pi over 3, and add pi n, where n is any integer, 0, positive, or negative. If n equals 0, you stay here, negative pi over 3. If n is a positive integer, you're adding plus pi n, remember. If n is a positive integer, then you're going counterclockwise by half revolutions. If n is negative, you're going clockwise by half revolutions. But we're picking up all the solutions along the unit circle corresponding to this point and to this point. This is perhaps the most compact solution set, form for the solution set. And again, we could graph this. Y equals tangent of x, which have snakes. Y equals negative root 3, that horizontal line. Where do the green and purple graphs intersect? Let's see, over here at 2 pi over 3, look at that. Over here, negative pi over 3, look at that. And they're coterminal twins. All right. Again, you tend to get this pi n setup, plus this plus pi n deal when you're dealing with tangent and cotangent, because you have that different periodicity for tangent and cotangent. You often get this plus pi n type pattern for tangent and cotangent. Although sometimes you see it for sine and cosine as well. For example, if your solution set consists of all the reps for this point and this point, okay, well, your solution set is basically of the form pi n, where n is integer, and this is the solution set for the equation sine of x equals 0. So it's not just tangent and cotangent, but it's true that you often see plus pi n when you're dealing with equations in tangent and cotangent. But you also see that in other equations as well. Next up, what happens with quadratic forms and beyond? Next time.
Well, that's going to be for our next session. Okay, I'll take questions now. Now, watch my note coming up. All right, now, if you're brave and if you're all caught up, in fact, if you, this is ideal. After this video, you can do all the homework through 5.31J. So if you're super conscientious, right, you want to be right on target, you can do everything through that point if you're following the videos. If anything, right? Of course, I know you're concerned about the Chapter 4 homework, which you're turning in next Wednesday. Actually, you might want to do section 5.3 first, or at least start it off first. Maybe do 5.3, 1A through J, because that kind of thinking, solving basic trig equations, that will help you in 4.7, perhaps more so than 5.1 and 5.2 will. Those are more algebra, the identities. Actually, 5.3 will generally be more helpful on the Chapter 4 homework. So I encourage you to actually do 5.3 before 5.1 and 5.2, actually, up through 1J. All right. So I'm running 12 right now. Okay, so we're done with the videos and my commentary. At this point, I'll start off taking questions on Chapter 4, presumably. If you have questions on today, that's fine, right? Okay, well, today's Thursday the 22nd. We'll spend the full day on Chapter 4 on Tuesday the 27th, further evidence that I think this policy of going over homework as opposed to giving you exams, I think you're learning more this way. I mean, having that whole day to talk about the homework, the fact I can link between, like the way I grade your homework and I can link to pieces of the video, that's awesome. I think I'd rather do that than give you exams. All right. Well, from the syllabus, I'm saying no exams, right? So it's in the syllabus. And by the way, when I said in the syllabus that I might change the grading scheme, what I mean is that the way I grade the homework, the particulars, right? So completeness, it was 1/2 the points on the chapter 1. It may or may not be 1/2 on future homeworks, right? So the particulars of grading the homework might change. All right, so that's enough of me. It's time for you. Those are the videos, so some of you might want to go. That's fine. You're very welcome, yes. I will stay around for questions. Because you remember, and I don't know if it's intentional or not, but when I decide which problems to grade, I may have a tendency to hone in on the problems we do in the videos, like after class, but that's okay. Right. Again, I did email you your chapter 1 grades. If I didn't, let me know. So for some of you, good night and thank you. I'll stay. Right. So I have 9:14. So I tell you what, I'll wait until 9:16. You're welcome. I'll wait until 9:16. And if you don't have anything for me in chat or by voice by 9:16, then we'll take a pause till 9:20. All right. It's your class. Okay, I'll wait for you. Okay, so I have a request here. All right, 477B. All right. Where's my? I can. Okay. Here we go. All right. Okay. And again, I'm still recording. If for some reason you want me to pause, let me know. So you said 477B, right? Right. 477B. Well, no, on these, you need to think. On inverse trig, you want to sit down and think because students rush through these things when they shouldn't. Ah, yes, very good. Perfect. So this is what I was referring to. The skills that we're talking about in 5.3, it's right here. We're solving some basic trig equations here on these limited intervals. So our 5.3 skills will be great here. This is a great follow-up. All right. You see, that's the thing. They look easy, but no. Be conscientious. Calm down. Think it through because too many students rush through these things. All of 4.7. All right, 7B, you asked in particular, and this was tricky. When the number here is negative, it can be tricky. All right, we want to solve. Sine of theta equals negative 0.3. First of all, let's observe that, yes, this is a legitimate sine value. Negative 0.3 is in the range of sine. If we had here like -3 or -10, we'd have the empty set, right? But this is a sine value. We are going to get a solution, I think a couple of them, in these intervals. I'll start with radians. Okay. Okay, so let's consider the unit circle. I'll go to blue. All right, let's consider the unit circle. All right, the sine value we want is negative. Do you know in which two quadrants is sine negative? Our solutions will not be quadrantal. In what two quadrants is sine negative? Think y-coordinate. In which two quadrants is the y-coordinate negative? Negative. It's going to be quadrants. Yes, very good. Quadrants 3 and 4. Very good. Okay. So negative 0.3, just to make it visually kind of accurate, okay? We're looking at this point here and this point here. But you know what's going to help? The reference angle will help. So in green, let's think about the reference angle here. I'm going to dash this line segment, this radius. Okay, so I'd like to know a nice acute angle, a reference angle, whose sine value is positive 0.3, all right? And in fact, we can get that by taking the inverse sine or arc sine of positive 0.3. The inverse sine or arc sine of 0.3, and you can get some approximation on your calculator. I say here, let's say we're dealing with radians. We're going to round off to 4 significant digits. And for the first time, I might want to break out my own calculator. Okay, now make sure you're in radian mode. Make sure you're in radian mode. Okay, for now. Do I know my own calculator? Okay, go to radian mode, know how to do that. Okay, and you want to find the arc sine of positive 0.3. Inverse sine of positive 0.3. Okay, do you see what you get? Are you able to get the inverse sine or arc sine of positive 0.3? What do you get to 4 sig figs? Do you see? Are you able to get it to 4 sig figs? Very good. That's what I'm getting. Right. And you're making me feel good too that I got it right, I guess. So this turns out to be about 0.3047. You don't have to put the 0 in front. 0.3047. I'll type it out. I'll put 0.3047. The 0 there is optional. All right. But this is not one of our solutions, right? Because the sine value there is positive 0.3. But this is the what angle for all our solutions? It's going to be the reference angle for all of our solutions. So even though this is not a solution in and of itself, it's the reference angle for our solutions. So even though this is not a solution, it's often very, very good to find the reference angle. The reference angle is extremely useful information. Okay. Now here, I want to know solutions between 0 and 2 pi. So at first, if I were to ask you, what's a representative for this point? Okay, well, an easy answer would be, I'll put this in red. Okay, an easy answer might be, well, how about negative 0.3047, which is a representative here, but the problem is that it's not in that interval. I don't want negative solutions. So I want to ask you, instead of this angle, I want a coterminal angle. Whoops. I want to add a coterminal angle. I want to go around the world once counterclockwise. Do you remember, how many radians do you add if you do one full revolution around this circle? How many radians do you add? How many radians in a full revolution? Good. The answer is 2 pi. And I'll do what you did. I'll put 2 pi. It's kind of hard to write the pi, right? Okay, it's going to be 2 pi. It's going to be, well, it's going to be about 2 pi minus 0.3047. This is an approximation. We technically have squiggles, but don't freak out about that. So what's that? All right. What's a good way of doing that? Going negative. Can I take the opposite easily on my calculator? The opposite of the answer? That works. Like if you take the opposite of the answer and you add 2 times pi. All right. I think I have this in the answer sheet, but what are you getting? I think it's in the answer sheet. Yeah, you're right. And let me verify on my answer sheet. Yes. Yes, we're doing 7b. Whoops. Right here, right. So we get the 5.978. Very good. Okay, so this is about 5.978. Remember, it's in radians. You don't have to put radians because that is the assumed unit. You don't have to put radians. So we have about 5.978 radians. So that gets us this over here. But wait a minute. Oh, any questions, by the way? Okay, we know, okay, so we believe that. About 5.978, we believe that. All right. But now, this guy here, we're going to get a solution here, right? I know there's an angle between 0 and 2 pi that's sitting over here. But it's hard to get it from, it's hard to move from one solution to the other. We're going to start where? We're going to start with the reference angle. So that's a key hint for a lot of these problems and a lot of these pieces of problem 7. When in doubt, figure out the reference angle, and then you build off of the reference angle, okay? So from here to here, we take 2 pi minus the reference angle. I have a question. I'll do this in red. How do we get from this reference angle, hint, to this over here? I add how many radians? Not 2 pi, but how many radians for a half revolution, counterclockwise? Very good, pi. Because, of course, this is confusing to students, right? They're going, oh my gosh, do I take pi or 2 pi? Do I add? Do I subtract? Work with the unit circle. I mean, as a teacher, right, if you're to ask me, hey, quick, Ken, what do? I have to draw the picture. I'd have a terrible time working these out if I didn't draw the picture first, right? I always draw the unit circle when I deal with these kinds of problems, okay? Anyway, so what's our approximate answer? We're going to get approximately, right? The 0.3047 plus pi, which is what? The 4 sig figs. Is that right? That's what I'm getting, 3.446. Very good. If you're off in the last decimal place, that might be a rounding thing. Don't freak out about that. But I think we're on the same page. 3.446. About 3.346. All right. And in this problem, I'm asking, find the two solutions. I'm telling you there are two solutions. Technically, in section 5.3, I would have you use braces, right? I'd have you use braces. I'll do this in red. In section 5.3, I'd want you to use braces, and then instead of and, you'd have a comma. All right, because remember, when you solve equations in section 5.3, your answers are solution sets. So here it'll be, in section 5.3, it's left brace, this number, comma, this number, right brace. You don't have to do it in 4.7, but in 5.3, I would expect you to write solution sets when you're solving equations. All right. Oh, yes, you're welcome. And again, the key is the reference angle. If you feel lost in this kind of problem, focus on the reference angle. How do you build from the reference angle? All right. Very good. And I think that insight will help you with the rest of these problems. Very good. But by all means, let's discuss this either tonight or on Thursday, perhaps, if you have further questions. Okay. By the way, chatting to see if students are locating their problems. All right, questions. Oh, okay, I see. All right. Okay, so it's 9:26, but I'm wide awake. I took a 2-hour nap I got up from recently, so I'm awake now. Any questions? At 9:20, oh, you're welcome. At 9:28, I'll pause and come back at 9:31 if there's nothing right now. Thank you. Yes, you're welcome. I appreciate your hard work, all of you. All right, any questions at this point? So let's take a pause. I'll return at 9:31, okay? At 9:31, I'll come back and I'll see if there's anything that you want me to wrap up, okay? I'll pause the recording now.